Read Piazza for discussions about the assignment. We're trying to clear things up, make things easy. They're not trying to be tricky. So if it looks as though it's tricky, then ask. Okay. Anyone have any questions about anything before we start here? Yes? A frame constraint is a specification that I'll go to the slide. Hang on. No, show. It's a specification of what doesn't change. But let's go through it again, because I went through it quickly. Sorry. It's way at the end here. So at the end of last time we did this. I think the easiest way to do it is this example. So frame constraints, so we have preconditions are like the preconditions we had in strips. Effects are like the effects we had in strips. But strips also has this assumption that, what we call a frame assumption, that says that things don't change unless they're specified. And this frame constraint is doing that. What doesn't change remains constant during an action. So here's the easiest example. So if Rob has mail at any time if it had mail before and the action wasn't what? Right, so which actions directly affect whether Rob has mail? Right, pick up mail and deliver mail, right? So if the action wasn't to pick up mail or deliver mail, so then the constraint is that the robot has mail at time I plus 1 if it is equal to the value that it had at time I, if the action at time I was not to pick up mail or deliver mail. So it specifies what doesn't change. Okay? And that's violated when the robot has mail is different and the act is not equal to pick up mail and not equal to deliver mail. So that's how it can prune things. But that's going to be part of the effect. So this is actually the value whether it's true or false. So this specifies the value whether it's true or whether it's false, this means. Not just that it's true. Okay, so this says that here it's trying to say that the value is the same value.
Well, I just read it as if he has mail, then he'll still have mail unless there's changes whether he has mail or not. Or the changes
Well, it should. Whether Rob has mail, well, Rob has mail any time if and only if it has mail before, it should be then. All right, I'll fix that. Well, it does change it, but that's part of the effects. So this is sort of effectively happens. It's not changing. This Rob has mail before is not changing if the actions were these two things. And that's important because that's not covered by the preconditions or the effect. We have to explicitly add in this thing that doesn't change, right? Because it was just an assumption in strips, but here we have to make it explicit. Right? This fact that things don't change unless an action that changes them. Okay, so it was just an assumption we said in strips, but now we're making it explicit. Any other questions about that? All right. Good. All right. Oh. I think I just killed something. And let's. So what we've done so far in the planning is we did the strips, representations defined in terms of these preconditions and the effects. And the strip's assumption is that features not mentioned in the effects are not affected by the action. So that's this assumption. And it's because making that assumption explicit is what we had to do in order to do these, to do the CSPs. So in forward planning, the nodes are states and the arcs are actions. In regression planning, the nodes are subgoals and the arcs are actions. And then we represented planning in terms of this constraint satisfaction problem for planning horizon of k. So we're going to look k steps ahead, k actions. There's going to be a state variable for each feature for each time 0 to k. And there's going to be an action variable for each time from 0 to k. So we can think of this as the state at time 0 and the action at time 0, and then the state at time 1 and the action at time 1, all the time up to the action at time k minus 1 and the state at time k. Right, so you can view it as this. These are these variables. These are a whole lot of variables. There's a state variable, and there's an action, and there's states. Okay, is that any questions about that? All right. So we're going to use this example again. We're going to do some clicker questions. So the planning problem has 5 features and 6 actions. And the CSP problem for planning horizon of 8 has how many CSP variables? You don't have to do any arithmetic at all. Is it 5 times 6 times 8, or 5 times 9 state variables and 8 action variables? 5 plus 9 state variables and 8 action variables? Or 5? Okay. Does anyone need more time? Does anyone still need more time? The number hasn't changed for a while. Okay, 3, 2, 1. Well, that's exciting. Oh, that's exciting. All right. So let's go through and let's see what this looks like. Let's go back to this one. So here it is for time horizon 2. Right, so at state 0, how many variables are at state 0? Right, there are 5 here. How many time variables are there for action A0? So how many variables are here? How many variables are there? No. Remember, rectangles are constraints in this diagram. There's just one. And how many is at state 1? 5. And how many at action 1? 1 plus 1 plus 5, right? Right, so there are 5 state variables, 1 action variable, 5 state variables here, 1 action variable here. So let's go back to, it's just here. So how many 5s are there? Are there? What was it in this case? How many? There was 2 steps. How many fives were there? How many state variables are there in total? In this one on the left side. Conscious counting. You learned how to do that. How many are there? How many state variables are on this diagram on the right? 15. Right, there are 15 state variables on the right, and there are 2 action variables. There's action at time 0 and action time 1. So how many state variables are in here? How many state variables are in here? Come on, what is it? This one. No. 5 times k plus 1, right? Wasn't trying to be tricky here. This was right. So there are 5. And how many action variables are there? There are just k action. How many action variables? Are there? Yeah, someone said k, I heard. There are just k of them. So the answer here is B. Okay? Does that make sense? Yes?
How do we decide what the k should be?
Here, k is horizon of 8.
Yeah, but when we're actually trying to solve a problem.
Oh, you start with small numbers and you do incrementally add it. So you try it for you guess a number of steps, and you can incrementally add it like you do an iterative deepening. So you can start off with, can I do it in 5 steps? Can I do it in 6? Etc. Okay, so what was the answer here? B. All right. All right, next question. The best way to learn these things is to debug yourself, right? To try things and experiment and not do it. So the action deliver coffee, whoops, let's put this back to here. The action deliver coffee has preconditions that the location is the office and robot has coffee, and the effect that robot has coffee is false and Sam wants coffee is false. And all I want to know is what the precondition constraint involves which variables. So it involves the action at step I in all of these, and involves the action at step I. What other variables does it involve? A robot has coffee at the next step, or robot has coffee at the previous step, or all right, how are we going here? Does anyone need more time still? Yep, okay. Okay, does anyone still need more time? 1 or 2 people. Okay. How about 5 more seconds? 1, 5, 4, 3, 2, 1. Put your yes guess in there. Okay. Stop. So the precondition involves the steps before, so the location before and the robot has coffee before at the same time. So it's at the ones before the action. So action 1 is S1, so the answer here is A. Right, so it depends on the robot has coffee and the robot location. Right, beforehand. And it doesn't depend on the location. Sorry? It doesn't depend on, what's C here have in it? Robot has coffee. Doesn't depend on whether Sam wants coffee. It's only the preconditions. It's only the preconditions here that do it. It doesn't depend on whether Sam wants coffee, the fact that you can deliver coffee. And that's the precondition again. I'm glad everyone got it, that it doesn't depend on future steps. Right? It only depends on the previous time. Okay, any questions about that? Okay. It's the same action, deliver coffee, the same preconditions and effects. We want to know what the effective constraint is this. What's the effect of deliver coffee? Which variables does the effect depend on? What does it constrain? So we want to know about the effect of delivering coffee. All right, does people need more time? Does anyone still need more time? Okay, 3, 2, 1, last call. Yay! Okay, the answer is E. It only depends on, it's a constraint between the action and the next Sam wants coffee and the next robot has coffee. Because once you have the deliver coffee, it has these effects of the Sam wants coffee and whether the robot has coffee. It doesn't depend on the location because the precondition affects the location is affected by the precondition, and it also affects whether Sam wants coffee. So B is not the right answer. Any questions about that? Okay. So robot has coffee, has the same value at time I plus 1 as it did at time I. When? A, always. B, never. C, unless the action was to deliver coffee and Sam doesn't want coffee. D, unless the action was pick up coffee or deliver coffee. Or E, unless the robot's location was the coffee shop or the office. So when does robot have coffee have the same value as before? At one time and the next time. All right, does anyone need more time? It's about all, yep, okay. It's actually not meant to be a tricky question. It's just I just wanted to get it for the, okay, 3, I'll stop, 3, 2, 1. Right. The answer is D, unless the reaction was this. So robot has coffee remains the same unless the action was pick up coffee or deliver coffee. Okay. Any questions about that? We're going to use that for the next question. Now, the frame constraint for robot has coffee was the frame constraint's going to specify effectively is a constraint for robot has coffee that specifies when it doesn't change. Right? Involves which variables? So the frame constraints can specify robot has coffee. I want to know what variables it's constrained by when it doesn't change. All right, does anyone need more time? Okay. Do anyone still need more time? Okay, okay, 3, 2, 1, we'll stop. Oh, that's exciting. So A and C got the answer is A. Because all it's doing is this is just the axiomatization of this previous question. Right? That the only thing that affects whether the robot has coffee is the action. The only thing that affects whether it stays the same is the action. So this is trying to be the same question as before. So this frame constraint specifies that the robot has coffee at some time. So it specifies this one. We just did this. Is that robot has coffee? That's robot has mail, but it's the same question. Robot has coffee here is the same as this one. So it's a constraint between the robot has coffee at time I plus 1 that has the same value as robot has coffee at time I if the action wasn't to deliver coffee or pick up coffee. Right? That's what this frame is saying when it doesn't change. Right? So the frame constraint specifies things that don't change. Okay? The precondition constraint satisfies the precondition, what's on the preconditions, and the effect constraint satisfies what happens with the effect of it. But we need more than that because we need to make sure explicitly things that remain the same if we don't change them. Are there any questions about that? So it's just what doesn't change. Okay. Any questions? Good. Oh, it's the wrong slide, wrong lecture. All right, hopefully that's clear now what's going on. So we just have these constraints about the effect, the precondition, the effect, and the frame, what doesn't change. Okay, so what we're going to do today, is there any other questions about planning? Because we're going to start a new topic now. Because we're going to give up this assumption of knowing everything about the world and having perfect information. So the rest of the classes, we're going to look at how we're going to reason when we have uncertainty in here. So at the end of the day, we're going to justify the use and semantics of probability. We're going to know how to compute marginals and apply Bayes' theorems and identify conditional independence. And I know you're supposed to have done a course on probability. Who's done a course on probability? Who hasn't done a course on probability? I thought there was a prerequisite to something like that. Oh well, you'll learn it. This is the quote at the start. I thought this was a nice quote from Steven Pinker. The mind is a neural computer fitted by natural selection with combinatorial algorithms for causal and probabilistic reasoning about plants, animals, objects, and people. So that's what we're going to talk about, is causal and probabilistic reasoning. And in a universe with any regularities at all, decisions informed about the past are better than decisions made at random. This has always been true, and especially we would expect organisms, especially infimivores, which are ones that consume information, such as humans, to evolve acute intuitions about probability. The founders of probability, like the founders of logic, assumed that they were just formalizing common sense. So that's what we're going to do today. We're going to formalize common sense. Okay. So what we're going to do is, the assumption we're going to do is agents don't have complete knowledge about the world. They need to make decisions based on their uncertainty. And it isn't enough just to assume the world, you know what the world's like. A good example is wearing a seatbelt. So if you assume you're going to have an accident, then you probably wouldn't go on a drive at all. And if you assume you are going to have an accident, you probably wouldn't go out and drive. If you assumed that you're not going to have an accident, you wouldn't wear a seatbelt. In neither case would you wear a seatbelt. But it turns out, because we live in a world where we're uncertain about whether we're going to have an accident or not, it's good to wear a seatbelt. Right? So if you knew, you wouldn't wear a seatbelt. But because you don't know, you're going to wear a seatbelt. So your actions change because of you're uncertain about the world. And the agents need to reason about uncertainties. That's what we're going to look at. So there's lots of uncertainty about the world, but agents still need to act. And you're going to make predictions about what's going to happen. So we're going to make predictions about whether we're going to have accidents. We're going to make predictions about the effect of some particular steering motion on our car. The doctor's going to have predictions about the effect of giving a patient some drug or some other treatment. You can make definitive predictions. You'll be run over tomorrow. You shouldn't believe that. If someone predicts you'll be run over tomorrow, you shouldn't believe them, because if you believe that you're not going to run over, then you'll be reckless and you probably will be run over. If you believe you will be run over, you'll probably be so scared that you won't walk anywhere, and so you won't go anywhere. So in neither case should you believe them. You can have point probabilities. The probability to be run over tomorrow is 0.02, or if you're not careful, or maybe it's less if you're careful. So you can have point probabilities. Or you can have probability ranges. So there's all sorts of arithmetic, all sorts of calculi that people have suggested for probability. But there's good arguments for using probability. Is that agents who don't use probability will lose to those who do. There's a very famous argument called, for Dutch books, is an argument that says that if you're gambling and you don't use probability, you're going to lose to someone who does. So every deviation from probability is going to make you lose all the time to this. So a book is sort of bookmaker does in races and things, and a Dutch book. I don't know why it's called a Dutch book, but it is. Okay. So there's all these good arguments. We're not going to go through them. And the other reason is we can learn them from data. And we're going to talk a little bit about how we're going to use Bayes' rules, going to specify how data and prior knowledge can be combined. And what we're going to mean by probability is the measure of belief in some proposition, what's called subjective probability. And an agent's belief depends on its prior assumptions and what it observed. So here's a coin. So if I toss this coin, what's the probability it's going to land heads? So half, say, right? I'm tossing it. So what's the probability it's heads? 50%. I'm looking at it. Has the probability changed? Yeah, from your perspective, it hasn't changed. From mine, it has, right? And I'm telling you it's heads, so so what's your probability that's heads? Yeah, I'd believe him. Yeah, because I lied. Okay, it's tails, but... All right, so that makes sense. So it's just a property of our information about what we're going on here. There's nothing... Right, so it's a property of just our information, our beliefs about things, and that's what we're going to do. All right. So what we're going to do is we're just going to measure this thing called belief in terms of a number between 0 and 1. We're going to call the probability. Probability of 0 means it's believed to be definitely false, and the probability of 1 means it's definitely true. And 0 and 1 is just a convention. Right? It's not anything else. It's nothing special or fancy about 0 or 1. And if it has a value between 0 and 1 means that you're ignorant about the actual truth value of something. So it's not so between 0 and 1 is you're ignorant of the truth value. And in some sense, this probability is a measure of my ignorance. So it's a measure of, and if the reason it was probably a half was because I was completely ignorant, because I just threw up my hands and said, I can't make any prediction. Each one is equally likely as far as I'm doing. It's not a measure of degree of truth. It's a measure of our ignorance or what we know. Okay, so that's what we're going to talk about, this belief. So we're going to talk about random variables. These are just like the variables we saw for constraint satisfaction problems. And so this should be familiar to those. We're going to talk about the range of a variable. It's sort of sometimes used the domain. Here we're going to mean the range in the sense of the mathematical term as a function has a domain and a range. So range is just a set of values it can take. We're going to talk about, sometimes we're going to talk about tuples of random variables. So is that some complex random variable where the cross product of all the ranges? So we're going to talk about that a number of times. It's nothing fancy. It's just the height and the weight of someone, or the amount of rain. If we'd have the rainfall today is a Boolean, it's going to rain, and the temperature, the maximum temperature tuple might be just a pair of them. Okay, there's nothing. We're going to write assignments just like we did before. It means variable x has value x. A proposition is we're just going to assign assignments of values to random variables. Okay. So it's just what we did for constraint satisfactions. So possible world specifies an assignment of one value to each random variable. And the other way to view a random variable, it's a function from possible worlds into the range of the random variable. So there's this possible worlds and random variables. So possible worlds can be defined in terms of random variables, or random variables in terms of possible worlds. And we're going to use this funny notation that's the same symbol we used before, as that W is a model of x equals x, means variable x is assigned, variable big X is assigned value little x in world omega, or let's just say W. So world W entails that x is equal to x. So that just means it's just the way we're going to do it. And we're going to have logical connectives are going to mean this what they did before. We can write on the right-hand side of this model symbol, we can talk about that alpha and beta is true in world. If alpha is true in the world, then beta is true. And this V symbol is this alpha or beta, and not is true. W is true if not alpha if it's not true in it. And we're going to let big omega be the set of all possible worlds. So just there's this funny symbol, it's just what's true in there. We'll just use it in a minute. Now probabilities are completely defined by this thing called a probability measure. It defines what's called just a function from sets of worlds into this non-negative real number, such that the measure of all the worlds is 1. And if you have two disjoint, if you have S1 and S2 that are disjoint, the measure of these, of the union, is the sum of the measure of those worlds. So that's all going to mean. That's the complete semantics of all we're going to mean in here. And so in the measures, the probability of any alpha is the measure of all the worlds where alpha is true. So the probability of alpha is the measure of the worlds where alpha is true. So here's here's 10 possible worlds. So each little shape here is a possible world, and each singleton world of each one of them by themselves is 0.1. So it's just what I'm going to define it as. So we have this measure over possible worlds. We can say each singleton set has measure 0.1. So what's the probability of circle in here? Oh. Probability of circle, 0.5, 0.4. What is it? Yeah, it's 0.5. We won't even do it. Half of, right, because there's 5 worlds. It's the set of these 5 worlds. It's this set of 4 blue worlds. And I don't have an orange, so I'll use this. And this other world, right? And the axioms say I have this set of the worlds, I can break it up into these singleton ones. Okay, what's the probability of star? What's the probability that it's a star? I can't draw it. What's that equal to? 0.3. What's the probability of a triangle? Right, 0.2. What's the probability of orange? What's the probability of orange? What is it, quick? 0.4. What's the probability of blue? 0.6. What are the random variables in this? What are the random variables we've used?
Color.
Yeah. The random variables are what? Color? Color and what else? And shape. Okay, so these color and the shapes completely determine the worlds here. And we have a probability over circle, so the probability of color is either orange is 0.4 and blue is 0.6, and there's a probability for each of the values for shape. Because that's all we're going to do. That's all probability is. Any questions about that? Okay. So then we can write down, like we did before for propositional logic, we can write down some axioms that let us prove things about this. And there's only 3 axioms that define probability. That the probability of any A, for proposition A, is bigger than or equal to 0. The probability of any true, the probability of true is 1. And the probability of A or B is the probability of A plus the probability of B if A and B can't both be true. So anything you can prove from probability, you can prove from these 3 axioms. They're the only three things we're assuming. And if you want to suggest a different calculus, you don't like probability, then you've got to say which of these you don't like. Right? Because if you're disobeying one of these, if you're disobeying probability, if you don't have probability, you've got to have one of these axioms, it's got to be false. Okay, because this is the only 3 things we're assuming. Okay, so that's all we're assuming. So that's sort of pretty weak assumptions. All right. But now what's interesting about it is we're going to talk about how to revise our beliefs based on new information. So when we have new information, we're going to revise our beliefs. So an agent builds a probabilistic model taking all the background information into account, and that's called the prior probability. So we're going to start off with a prior probability, like the prior probability about a patient comes in, you're just a random person in the world, they have some prior probability. And then the evidence is all the information obtained subsequently. So the evidence is all of the bits of information that the doctor observes, what you look like, what you tell them, what's on your electronic health record, etc. And then the conditional probability of H given E, which we're going to define, is called the posterior probability of H. So we're going to update your probability based on this evidence E, and we're going to get your posterior probability. So we're going to use these weird terms. We're going to talk about evidence, priors, posteriors, and conditionals. Okay, just keep in mind they're the things we're going to talk about. So what evidence does? What evidence does is it rules out all possible worlds that are incompatible with E. So if we look here, if we have these possible worlds, we observe the color is orange, right? Then we're just going to get rid of all of these other worlds, and we only then have 4 worlds left. Right, so the probability in here, the probability of circle given orange is what? What's the probability of circle? Circle given orange is what? 0.25. Because all we've done is we just said orange is true, so we're only looking at the worlds where orange is true. And out of all these worlds, 25% of them have circle true. What's the probability of star given orange? In here, someone else? What is it? 0.5. So that's what we're going to do. We're just ruling out world. What we're doing is saying the world couldn't be like that. Because we've made observation the world couldn't be like that. And what we're going to do is we're just going to have a new measure over possible worlds where at some constant times, so the measure of the worlds, so there's a new constant given, this new measure given by evidence E. So the measure of any set of worlds is some constant times the original measure if all the worlds have E true. And it's 0 if all the worlds have E false, and that's all that we have. So that's all the definition to do. All we're doing is ruling out worlds. All worlds where it's false, we're just going to cut them off as 0, and everything else we're just going to renormalize them by a constant. And it's pretty easy to show that because for any set S, let's say, omega is the set of all worlds that entail E, the set of all W such that entails E, union the set of all W such that, such that E is false. Right, so the set of all worlds, this is the set of all worlds, is the set of all worlds where it's E is true, union the set of all worlds where E is false. And we know that mu of E of the set of all omega has to be 1. And we then know this is mu of E of these things, of the set of all W such that W entails E, union the set of all W such that W entails, such that E is true and E is false. And because we have this previous one, we have this one here that says that the union, if the disjoint, if it can't both be true, right, if these can't both be true, so this must equal to the measure of E of the set of W such that W entails E. plus the measure of E of the set of all worlds W such that the evidence is false. So the set of all worlds where it's true plus the measure of the set of all worlds where it's false. This thing here is equal to 0. This one's equal to 0. This one's equal to C times the measure times the measure of all the worlds where E is true. The measure of all the set of all worlds such that the worlds entail E. And what's this equal to? Let's try this off. What's this equal to? What's the set of all worlds that E is true equal to? The measure of the set of all worlds where E is true. Right, that's just the probability of E. So now we know that 1, we now know that 1 equals C times the probability of E. So C is equal to 1 over the probability of E. Whoops. Oh, we're good here. And now the conditional probability of a formula given this evidence is just the probability of H given evidence is the probability of H given this new measure. And now this is all the worlds where H is true, where E is also true. We can do the same thing, in which case we end up with this formula. The probability of H and E divided by the probability of E. Now this is normally given as a definition, but it's much better to think about the definitions. All we're doing is ruling out worlds, and then we have to renormalize so they're up to 1. Right? So this is often given, the probability of H given E is often just given this formula, but we really know what it means. It means that we've got all the worlds, we're just crossing out all the worlds where E is false, and we're just normalizing them all constantly. We're just expanding them up before. So that's all this conditional probability is doing. This formula at the bottom, which is often given as the definition, is not the definition. The definition we want to do is having this new measure over worlds. So all the worlds where it's false, we're just crossing them out. And how they have probability 0, and then we just have to renormalize them, and we get this formula. Because sometimes you get to tricky examples where you can't apply any formula, but if you know how it works, you can just work it out. Okay, so that's going to be important. So it's important that you know what it actually means. All right. We've run out of time. This is actually on the thing. Why don't you there's no class on Wednesday, is there? On Friday, we'll start off with this exercise of doing this because it's intuitive to make sure you know what's going on. So try this before Friday, and it's not tricky. All the arithmetic goes out. There's no complicated things in here. So let's stop here.